Okay, so nowadays we always use to define AI as a dual use or even a multi-use technology, which means that algorithms are mainly industry agnostic. So the mathematical models or the codes we are using can be used from one sector to a very different sector. And also, we no longer need to build every model from scratch. We have NLP models, that ChatGPT models that have been developed for develop language. That the whole idea about the speech and that they're studying around text has been developed, but they can be easily used in other sections, like modified to learn about genetics and about other sections. Then we have the tools that developed for high-tech sectors are rapidly trickling down, which means that you have models from industry like autonomous driving, with millions and millions, billions of dollars spent there, that can be easily used now on other sections like agriculture monitoring, etc. However, there is a catch. While this the engine is the same, the road is completely different. And one thing is, one size does not fit all. So although the model is the same and the mathematics, the code is the same, the objective in many times is completely different. And other thing is that we have to respect the data culture, which means the data, the way we use it, the biases, how we interpret the data, etc., are completely different. Also, there are several operational constraints. So models that have been designed to work on a big cloud data center, obviously we cannot directly take them and apply them to a device that is battery powered with very limited capability, etc., etc. So what I'm going to talk is about, can we move the screen because I cannot read half of it. If possible. Anyway, what I'm going to talk is I'm going to present some of the work we have been doing at Imperial College related to defense. So I'm going to present some AI-related defense problems. I will demonstrate some specific AI methodologies that we are using to solve these problems, and and explore some analogies between all these defense scenarios and some civilian applications. And also then differentiate and say how we have different objectives and different risks when we apply this to different domains and vice versa. And finally, I will conclude with what is the role of academic research within the whole AI R&D. Probably I will move a little bit because people cannot read. Oops. Let me. Probably getting closer rather than. Anyway, so the first AI application I'm going to talk is about how to identify hostile electromagnetic waveforms in defense-related environments. And this problem came to us before AI, when we were working with the Department of Defense in the US. So one of the scenarios you had there, they have their troops were going at that time the war with Afghanistan, and they had they tried to detect some remotely detonated explosives, and the problem was most of the time people were using there some garage remote control to detonate the explosives. And obviously this is easy to identify when you know what exactly this is, because if you're in the middle of the desert, there are no buildings around it, suddenly you have a signal like from a garage door, you detect that signal, you can identify what is happening. But most of the cases, you don't know what that signal is. So in congested electromagnetic environments, you have radars, sensors, communication signals, your troops are moving. At the same time, you want to detect any kind of hostile signal that does not belong to you, but to the enemy. Well, the problem there basically is that unlike the conventional, most of the AI machine learning techniques where you can classify the problem, when you have, for example, this is a cat or a dog, now we have to identify this is none of this. So we are dealing with data set we haven't experienced before. There are signals we haven't seen before. So what is the proper way to do that? The AI techniques we use is something is called anomaly detection. So we train our model to learn our own signals, so the signals from our devices or the device of our allies. And then whenever we sense, our model will try to flag any signal that doesn't fall with this category as an anomaly or a potential outlier. And I'm going to explain here in the other applications I'm going to talk later a little bit about the models. I try to make them as simple as possible for people to understand if you don't have any background on AI or machine learning. So one of the models we use there is a generative adversarial network. So when you go to the internet and you see all these AI-generated images, this is one of the models usually used to generate them. So this architecture comes with two components, the generator and the discriminator. The generator will try, let's put in the context of creating images, will try to generate an image of a person that looks as real as possible. So it will feed it to the discriminator, which together with some real photos of a person. So the discriminator will compare the synthetic, the fake image, with the real one, and will give an output, is it a real or a fake? It will give it back to the generator. And this will go on and on and on. At the beginning, you will have a photo that doesn't look anything like a human, but if you do it again and again, you will learn to generate images as close as possible to a human face. Okay. So in the AI, now what you have, they discard the discriminator, they use the generator to generate that images. But in our case, we don't want that. We want the discriminator because the discriminator has now learned how to identify a signal that is real or not. In that case, I was talking about was the human face, but in our case was electromagnetic waveform, which is time series of data, what the signal, a mobile signal, a signal of a sensor, of a radar, etc. And we use that to identify if something is hostile or friendly. Obviously, there are many challenges that the environment is changing over time. So new allies are coming, are joining our troops. We have new sensors. The environment is changing, and this makes it very difficult because we're going to have many false positives. Something that is very important because it can end up to having like friendly fires or identify Our own devices are something we have as adversarial. We have lots of red flags, and this is very crucial for this kind of application. So commercial applications now. What we use there, it wasn't new. It has been used before for financial fraud detection. Basically, how to spot any kind of sophisticated money laundering schemes, detect any frauds for your credit cards, etc., etc. It has been used as well. It is used for manufacturing quality control. So we have visual inspections of systems and on assembly lines, and we flag defective products. And these are defections we try to detect there that we haven't experienced before. We haven't seen them before, but with that technique, we can identify that this is something new, this is something that looks abnormal, and this is why we have to flag it. And you can see here the key difference. So in the commercial context, if we call the intent of that anomaly is usually accidental when you have in a manufacturing, or it's opportunistic when we talk about financial fraud detection. But in the defense context, it can be intentional. Adversarials, we have camouflage, we have people that try to jam our signals, etc. Then I talked about the false positives or false negatives. So the false positives tolerance is for a commercial context, this will mean I'm just losing some money. Okay, I'm going to discard a product that, or the user experience will be worse. In defense context, this can be very crucial, can lead to fratricide, which means like friendly fires, deaths, etc. And also the compute location. The one can be in a cloud-centric, we have lots of processing power, while in defense, it's end-centric. So it runs in small devices, battery-powered, and we cannot run very complicated algorithms. All of these affect both the training and the actual application of the AI algorithms. Another technique, another application actually we have was about self-supervising, applying of self-supervising learning. And that was on how to have real-time SAR decisions for scan data. SAR stands for synthetic aperture radar, which are like images. Think about a plane or a satellite that moves around the area. It takes many photos of the same object or the same landscape from many, many different angles. And we have that drones and satellites that continuously every day collect all of this data. And you have terabytes or petabytes of this kind of data under different type of conditions, night and day, through clouds and very adverse weather. But the majority of them are raw data, they're unlabeled. So we don't know what we collect, we just collect the data. It is very difficult to actually label the data. It is also, it is expensive, it requires also specialized expertise. And so what we want then, suddenly, we have a target that we want to classify, we want to identify something. And we know what it is, and we have a very limited number of labeled data. In order to train our models, usually we need big data. We need thousands, millions of pictures. Now we have only a few of them. How can we use only the few of them and all the others that they were unlabeled to train our model? So this will be our ground truth, what I described earlier. The ground truth, these are the labeled images, and from them we want to train our model based on the whole set. So traditional supervised learning techniques require thousands of labels and is too slow and impractical for involving tactical environments. How we use it? We use SSL, self-supervised learning. So instead of train our model in the actual objective, which was do the classification on the images, we do something else. We train on some other task, somehow related. So which do not require any labeling of the data. One of these is a puzzle solving. So we hide parts of our SAR images, and we ask our AI model to predict this, what is there. So our model will not learn what exactly are the objects or the terrains and the environment is learning, but it will learn textures, shapes, shadow patterns, etc. So when eventually we have some labeled, few shots of labeled images, we can just add a small part, a new component or our neural network model, and fine-tune it, and we will be able, based on that, to learn, based on the small number of labeled data, we learn to classify what we had and what we need to find. So this can be much faster and with much less data than before, which is very practical for this kind of applications. This, again, has been used in many commercial applications, in autonomous driving. So cars collect billions of hours of driving video, and then, based on that, try to learn the physics of the road. They don't use it that much for classification. They use it for predictions. What is going to happen next when you drive? We have it in medical imaging. We have rare diseases. Although we have thousands, millions of photos of X-rays, let's say, or MRIs, we have very limited photos, data from very rare diseases. So when you have that data, how can we train our model to identify this, that person has this kind of disease? Again, it's the same concept. We use SSL to learn the human pathology, the human anatomy, and then use that labeled data small number of labeled data at the end to train our model, fine-tune it, and do the classification. Again, key difference is the environment structure. For autonomous driving, you have very structured. You have a road and you have rules. People tend to obey like traffic on the traffic lights, green, red, etc. While in defense context, we have unstructured off-road cases. And also, it is the data integrity. It's most of the cases here. The data are noisy and honest. You don't have any artifacts that are intentional or deceptive like we have in a defense environment. Again, this affects both the training and the application of the AI. Another thing is how to do robust optimization using AI. And we use it specifically for what we call Internet of Battle Space things and network optimization. Probably you heard about IoT, Internet of Things. This is Internet of Battle Things. It's the ecosystem of huge number of devices that include sensors, satellites, communication devices. You can put thermal cameras or robotic dogs, etc., etc. They all move together, and they try to form a network that sends data, collects data, transmit and process the data. In order to optimize this network and any other network of that size, this is what we call this problem is NP hard, which means the complexity increases exponentially if you add one more component. If I add one more camera, if I add few more nodes in my network, the complexity increases exponentially. So the time to calculate the optimum solution increases exponentially. However, when we have in tactical IOBT environments, the network conditions are changing very fast. So what we manage to optimize our system on a particular case now, which is irrelevant 5 minutes later or a few seconds later. And this is very important. So previous optimal solutions become obsolete before they can be fully implemented. So this is the big trade-off, speed versus optimality. So our objective is to find solutions that are robust. We are not interested in the absolutely optimum, but we are interested in something that is good enough, but is robust. It will not change. The techniques we are using here is deep reinforcement learning and graph neural networks. So graph neural networks are particular architectures of neural networks that the kind of structure that can capture the structure of that we're interested in is communication networks. This is the IOBT. And they do that by just capturing all the important information and interdependencies between different components in our network and summarize them in what we call a vector at the end that has all the important information. And then we use reinforcement learning based on that actual compressed vector. So reinforcement learning, we have some agent that interacts with the environment. It gets some reward based on what it has done. It moves to new states and forward. So it's a kind of real-time optimization of the AI model. And the very important thing here is that we don't try to find optimum solutions, but we try to find optimum policies. So how exactly our agent will react. As an example, our agent may define how to route the information in our network, where to store the information, where to process the information, etc. So it's not going to be always try to use that node. This is why you should use that node. So this is how we deal with the trade-off, this about speed and optimality. And this has, again, many commercial applications, like the Amazon cloud systems. So you have, we can automatically reconfigure cloud resources against any kind of random failures that we couldn't do before. And also on-demand logistics, we have like real-time driver delivery and matching in dynamic traffic. Again, Amazon, they have big teams of people working in operation research dealing with these kind of problems. Again, it has some significant differences. So we have the disruption that in most of the cases here is random, but in defense it is more like intelligent adversarial. The objectives is changing. Instead of maximize profit and efficiency, you have to maximize survival and connectivity. The risk, again, here is financial and customer, how the customer is impacted by any kind of failures or suboptimal optimal decisions, while in defense context can be lethal and mission can lead to the failure of the mission. Again, both of them will affect the training, the data we are using, and also the application of the AI. Last thing is about the causal learning. And I will go very briefly because I think I'm running out of time. So what most of the machine learning models and AI I described before, they learn correlation. They don't learn the causality. For example, you run a campaign with advertisement promotion campaign in your company, and you find that it works well in this particular day. And you think, okay, the campaign went well because there is a high correlation. However, the cause of that may be something different. For example, there was a particular event or something happened with your competitor, etc., etc. So it is important to find what is the cause of what happened, not how this is correlated. The other is the simulation to reality gap. In the interview before, we heard about this, how we move from the simulated data to the real world data. There is a huge gap. Dealing just with the correlation creates lots of problems. So moving from correlation to causality, knowing the cause of this, of what is happening, why you react like this, impacts quite a lot and helps to move from simulated to real application. And finally is explainability. We don't want to have decisions that come from a black box model. We need to know why this is happening. And the causality can help us to identify that. Just to go briefly how we do it is using causal reinforcement learning again. We integrate causality with reinforcement learning. We build some causal graphs. These are graphs that they capture how exactly the environmental variables influence each other in our model. And then this will enable us to ask questions. So what happens if I do X instead of doing Y? So this helps the model to explore different possibilities. Doesn't go towards one direction, goes to different directions and learns why that directions impacted the overall model. And this has huge benefits, not only on defense, but also in personalized healthcare to identify which treatment caused this recovery for specific patients, etc., and also to do effective marketing campaigns. Again, the difference is the cost of failure, financial versus lethal, the data latency in many cases, and this is very important as well in defense. We cannot tolerate delays. Reacting to threats, it's very, very important. Which brings like a summary of all the actual differences. I talked about most of them. So we have cost of failure, the data availability that we have. This is also very important that we are dealing sometimes with privacy, which is, in many cases in defense, this is not an issue. Real-time latency, we have zero tolerance in defense. The goals of optimization of our model is changing. Instead of efficiency and profit and customer satisfaction, we have survival, resilience, and mission success. We need to be very robust instead of just optimum. And obviously the last one is very important, the compute location or also the application of the AI, which is not cloud specific most of the case, that we have big data centers running our models, the Google centers, the Amazon centers. We have to run this in the edge on small devices, and this affects quite a lot our models. And last, what is the role of academia in all of that? We have a dual mandate. We do not just do research, we try to train researchers on AI for the industry, for the future generation, for the nation, etc. So this changed the priorities a lot. So we focus on blue sky research many times, although many times very practical. Low technology readiness level research that we don't concentrate on the end applications, but mainly on the algorithms and how to make them work. The impact, what we measure, is not measured in profit, but is probably in publications, citations, and the societal impact. We value negative results, so disproving some theories, etc., is not always find something positive. Even a negative result is okay. So historically, academia was developing most of the main AI models that we have now. You can go back to the literature and see most of the models where they started. But the way we work is slightly different. We have small agile teams like PhD students. At the end of the day, the research is structured around this because every piece of research has to end up to a PhD thesis suitable for an individual. We have also bigger projects, but the majority of our projects are limited like this. But lastly, we have a lot of challenges now with particularly with where the AI research is moving towards big LLM models, huge data. Academia doesn't have the processing power, it doesn't have the capability to do that. We can still work on fundamentals, we can still work on the math, the algorithms, but we cannot compete with Google, Amazon, other big Facebook, Meta, etc., with due to these limitations. So, nevertheless, there are lots of collaborations between, as you can see from our research here, with academia, industry, and government bodies. And I think the future is if we combine everything together. I mean, this kind of collaboration create an ecosystem that we can work together and move forward. Thank you.